Okay, so in this video, kind of in our attempt to work through all the concepts you saw in linear electrical circuits, in this video, I'm going to go through the definition and concept of electrical current. Now, many of you guys took linear electrical circuits, and so you should know what current is, but that's okay. I won't assume that you've seen that before. We'll go through all the key concepts here. All right, so the key kind of mental picture is, I like to think of it as if you're going to the river bank to watch the water flow by. So if you go to a riverbank and you were to, bring your chair and, sit down, take a break, drink a soda, okay? And as you're sitting there contemplating the flow of water, what you could do is ask, drop in a slice. So you've got the water flowing. You should change colors here. So drop in a slice, and you might ask, okay, every second, how many water droplets are crossing that slice? So per second, how many water droplets cross past you? That's the concept of current. Okay? So in an electrical context, instead of a river, you're talking about a wire. And when we say the current is some amount, what we're talking about is the number of charges which pass a point along the wire, or more precisely, cross the surface. If you were to cut the wire, how many charges move through that surface. Okay, so I'll write that out now. Current is the rate that charge crosses a surface per unit time. Okay, so that's kind of interesting. It's maybe a little more complicated than you might have thought. It's some sort of unit of charge per unit time. So there's that. And it also has to do with geometry. So just like a river flowing, if it flows this way, it doesn't flow that way. So if you're sitting next to the bank, then you don't get wet. You only get wet if the water's coming at you. Well, the same is true with current. If you're sitting next to a wire, you don't get shocked. You only get shocked if your hand is kind of part of the wire, then it goes through you. Okay, so the current through you is what you should worry about. The current that doesn't go through you is somebody else's problem. So, okay, so it has to do with a surface and charge per unit time. So unit-wise then, current, the symbol for current is I. I'm going to use lowercase I. Sometimes people use capital I. To be honest, I may go back and forth just if I forget what I'm doing. And it's a charge. It's a change in charge per unit time. Okay, so current is a charge per unit time, which immediately tells us in SI units, current should be coulombs per second. And the name given to that is an amp. Or it's actually an ampere, but we just say an amp. So 1 amp is 1 coulomb per second. Now, interesting bit of trivia. In fact, in the metric system, the fundamental quantity that we use to standardize measurements is not Coulomb. Morally speaking, charge should be the fundamental quantity, and Coulomb should be the basic unit. However, in the metric system, a Coulomb is so big, we can't accumulate a Coulomb's worth of charge, so it's not convenient. On the other hand, 1 amp of current is a lot of current, but it's not impossible. And so we can readily make that amount. So instead of defining the Coulomb as the fundamental unit in the metric system, we actually define an amp to be the fundamental unit in the metric system, and we define a Coulomb to be an amp second, an amp times a second. That becomes the definition of Coulomb. And so in the metric system, Coulomb is actually a derived unit. It's an amp second, and amp is considered to be the fundamental unit. It's just a practicality thing about measuring, since we can't actually build up safely a Coulomb of charge. All right. So that's the idea. One other comment. Positive I measures the direction of flow of positive charge. So that's a historical accident or mistake, I guess, because we now know that electrons have negative charge. And so the things which actually move around in a wire carry negative charge. So when we say that we have positive current going one way, what we actually have are negative charges going in the opposite direction. So it's just kind of an annoying fact. It mostly doesn't matter, except when we get to the Hall effect and magnetic fields. Okay. So that's just so current measures positive flow. So the real true flow, the physical flow, is actually a counterflow going the other way. Now, let's talk about current from a bird's eye view, macroscopic. And basically, it amounts to charge conservation. So the key equation we're going to have is that if you have, imagine you have a wire going in connected to 2 other wires, and you have a current 1 and a current 2 and a current 3, where the arrows indicate the direction of positive flow. When you have a wire with an arrow, you're basically defining positive I2 to mean that way. Negative I2 would be going against the arrow. Right, so charge conservation says that all the charges have to be accounted for. Okay, so that means that if I put in charge on one side, this is just a wire, it doesn't have pockets, it's not like you can store charge. So if I have current going in on one side, that must balance the current leaving on the other side. And so we end up immediately with Kirchhoff's junction rule, which says the sum of the currents in must equal the sum of the currents out for every junction at a junction. And a junction is just a place where wires meet up. So current in is current out. And this is sometimes called Kirchhoff's junction rule, or I don't know, I get confused. Is this his first or second circuit law? Anyways. They're the current rule or current law. It really is just charge conservation, but the name Kirchhoff is attached to it. Okay, so that's kind of the macroscopic view that I wanted to provide on currents. I want to talk about what happens on the inside of a wire. It turns out it's a little more complicated than you may have thought. So, yeah. So the microscopic view so the microscopic view on currents is the following. So the idea is when you have a material like a metal, you have these little charge carriers, little things that can move around. So we have these little points which are free to move. And we're going to assume, I mean, we now know they're electrons, but let's just take it to be that these little charge carriers have some charge, we'll just call it Q. And furthermore, so on average, if I just have a piece of metal or something like that, some conductor, I have these charge carriers, they're just sitting there, and on average, nothing's really happening. We're going to assume there are capital N carriers per unit volume. Okay, so capital N charge carriers per unit volume. So that means, you know, in any chunk of material, how many charges are actually free to move around. In practice, for metals, is probably a good assumption that about one that each atom can contribute on average about one electron. So roughly, the number of charge carriers per unit volume is simply the number of atoms per unit volume. So it's like the number density of in a metal. But really, it should be the charge carriers per unit volume, and then, but you expect that to roughly be the number of atoms per unit volume, assuming that each atom contributes one charge to the flow. All right. Now, if we were to apply an external, if we were to apply an electric field to the metal, then what you would find is that rather than kind of the little charge carriers canceling each other out, their flows kind of zeroing out, what you would find is that in fact, the charge carriers would all start to move in the direction of the electric field. Now, in reality, they would kind of rattle around and bump into each other and bump into the underlying, you know, in a metal, there's usually like a crystalline lattice underneath. So they would rattle around. It's more like the Price is Right game, Plinko, if you've ever seen that. So they would kind of ricochet all around. And what would happen is, so there's going to be a lot of friction, I guess, is for lack of a better word. And what you would expect is that you apply this electric field, you know, in vacuum, then these guys would feel a constant force and accelerate, going faster, faster, faster. In practice, what happens is they kind of reach a terminal velocity where they kind of speed up and then they just travel at a constant velocity because of all the bouncing around and friction. And we call that average kind of effective terminal velocity that they have, drift velocity. So we assume that so we assume carriers move with drift velocity Vd with an arrow. Okay, so we assume that they move with a drift velocity Vd, and that would describe how fast they actually move. How fast they actually move through a wire or through a metal. Okay. I need a better system here. I don't have. Oh, okay. Here you go. I'll put our little spoon thing. I'll probably drop that and crack a tile. Great. Okay. Okay. All right. So now to understand what happens inside a current flow, what I want you to imagine is that, so there's a wire, okay, with all these little currents flowing. In reality, they're kind of bouncing around a little bit, but we're going to assume they all move with one velocity. And then we're going to kind of zoom in on this little spot right here. So I'm going to kind of imagine a little chunk of from inside the wire, a microscopic or differential sized piece. It's not going to be a big thing that you can see. You have to kind of imagine taking a limit. So I'm going to blow that up. So what we're going to have is I kind of drew a little chunk and I drew it as a little box. So I'm going to blow that up. Oh, okay. So what you should imagine, so the goal of this is, from the bird's eye view, the point of view is I have a current I, but I want to relate the macroscopic current I to the microscopic flow of the little charges inside the wire, and to really understand what's happening. So here's my little chunk, and I've kind of blown it up there. I'm going to assume the area of this, the area it's infinitesimal, so I'm just going to call that dA. And if I'm being really careful, I should say I should have a normal vector, and I would say there's a vector differential, dA vector, which is dA times the unit vector. Right, so that's the area differential to the surface. And so I have these little charge carriers. So there could be one over here. And the idea would be that in a time, delta t, lowercase t, how far would it travel? Well, in a time delta t, I would say, oh, the change in x would be the drift velocity times the change in time. So that would give you roughly how far each individual little charge carrier, Q, moves per unit time. Okay? So you should imagine then there are lots and lots and lots of these little charge carriers. Okay? Lots of these little charge carriers. And in the presence of an electric field, they're all going to flow. And okay, that's fine. And then I think to myself, okay, well, look, if I look at a little chunk here, and if I adjust the thickness of this little slab to in fact equal delta x, or in fact, if I make the width of this equal delta x, I should have said, dot n. So that's how wide this is going to be. But roughly what I'm saying, oh, okay. Then if I do that, then I've chosen this little slab to be sized so that every charge which starts out inside that box will flow through this surface in a time delta t. It can be guaranteed. Basically, I assume they're all moving with this velocity in this direction. And if I adjust the width of the box to have this thickness, then everybody inside it will pass through surface, or this surface dA in time delta t. Okay, so I can then say, okay, how much charge passes through this surface? How much charge passes through the surface? Because I'm working towards the concept of current. Well, the amount of charge that passes through that surface in time delta t, well, that's just and these are all differential things, so I better call that di. So that the differential, sorry, dq, the differential amount of charge which passes through the surface, well, that's going to be the charge per unit volume. Sorry. It's going to be the number of carriers per unit volume times the charge per carrier times the volume of this little slab. That's going to tell you how many charges were inside that slab, but I know that every charge that was inside that slab eventually crosses through the surface. So let's write that down. So I have my little slab, and I found that dq was the charge, the number of carriers per unit volume. I'm calling that capital N, times the charge per carrier, that's just Q, times the volume of that slab. Well, I said it had area dA, and it had thickness given by delta x dotted with N. Or using the fact that delta x is related to the velocity, I can write this as NQ. It's an unfortunate symbol. This is the charge flowing through it. This is the charge on a charge carrier, on one charge carrier. Anyway, times dA times the drift velocity dotted with N times time delta t. And what we learn is that the contribution to the overall current that this little chunk of volume makes is di, because it just makes a little baby step contribution, equals, I'm going to write it out as, so that's going to be dq over dt. So I'm going to pull the delta t over, and this will just be N times Q, this is the charge carrier's charge, times Vd dotted with N dA. Okay. So this is, so I had this sort of chunk, and this little chunk contributes this amount to the total current for the whole wire. And if I wanted to get the total wire, what I should do is add up all little chunks going across the wire. So kind of, if you have your wire, you would want to add up over all little chunks, but that amounts to integrating over the area. So if you integrate it over area, you get the current. Anyway, so this can be written as di equals, now this quantity right here is called J. It's called the current density, and this is nothing other than dA vector. So the current density determines the current per unit area in the direction of a surface. So if you want, you could say the current is the flux of current density through a surface. Integrating this up, we learn that the current equals the integral of di, which is J dot dA. So the current is the flux of current density through a surface. What you're really saying is nothing other than thinking about water flow. Okay, if you knew, so you would have like a number of water droplets per unit area that flow in a certain direction. And if you want to know the total amount of water through a surface, you would basically multiply the number of droplets per unit area in that direction times the area of that. Well, that just becomes, multiplying by area just becomes an integral. And so you're integrating the current per unit area in a certain direction over a surface. So that is so that defines implicitly, though, the concept of current density, and it gets the idea of current and how it relates to the actual motions of the underlying microscopic charge carriers. So let's do a simple example. Let's assume we have a current of 1 amp and let's assume that the drift velocity was close to 1 meter per second, roughly 1 meter per second. So we're going to have a wire, okay, and we're going to have all these little particles moving around at roughly 1 meter per second, we assume. Furthermore, let's assume that our wire is made of, I don't know, what's the atomic number for, let's say the wire is made of, well, let's see. I need something that I know the density of. I tell you what, we'll solve for it. So we've got this material. We know the current is 1 amp. We know that we'll assume the drift velocity is about 1 meter per second. Let's assume that Q, the size of the charge that each charge carrier carries, is E. Okay, so we have that. And okay, and let's assume the wire has a diameter of assume the diameter is 2 millimeters in width. Okay, and the wire, we'll take it to be a cylinder. So what I would like to do is estimate what is the number, what is in for this material. So assume you have a 2 millimeter diameter wire carrying 1 amp of current of charge carriers, which are, have charge, each have charge E, and assume they have a drift velocity of roughly 1 meter per second. All right. So let's do that. So what I would say is, okay, so I would look at my formula for J. The formula for J is N times Q times the drift velocity. So that is N times E times 1 meter per second to the right. So I'll call that X hat. And that's fine. So if I have my wire and I want the current to be 1 amp, what that means is that if I draw a vertical slice, like I break the wire like that, so there would be kind of a cross-sectional area, which would be a circle. If I slice through that wire, that means that 1 amp of charge, so 1 coulomb of charge per second, flows through that. And the formula for current, I, is the integral of J dot dA. Well, okay, J points in the X hat direction, and dA points in the X hat direction. So that's nothing other than N E times 1 meter per second times the area of the wire. So that's says, kind of pulling, I guess I'll write drift velocity, VD. Okay. So if I solve for N, that equals I divided by E divided by the drift velocity divided by the area of the wire. And so plugging in my numbers, I'm going to say 1 amp, that would be 1.61 times 10 to the negative 19 coulombs times the drift velocity 1 meter per second times the area of a wire. I said the diameter was 2 millimeters, so that's going to be pi times diameter squared. To the negative 6, right? 2 times 10 to the negative 3 squared becomes 4 times 10 to the negative 6, and I have to divide by 4 because I use the diameter. So that cancels that. Type it in here. I've got a calculator somewhere. And I get a number density of 1.96 times 10 to the 13, and that would be carriers per unit volume. So number of charge carriers per unit volume would be like 10 to the 10 to the 13. So how can we estimate that? Well, I claim you should get something roughly 1 charge carrier per atom. So this would be the number of atoms per unit volume, roughly. So it'd be carriers per meter cubed. Well, how could you estimate that? Well, the volume, if I think of an atom as roughly spherical, the volume of an atom, of one atom, so the radius of one atom is like 10 to the minus 10 meters, which means the volume of one atom is like 10 to the minus 30 meters cubed. Oh, I fouled this up. I apologize. Let me try that again. No, 1.6 times 10 to the negative 19. I have to be careful with my parentheses. 5 times 10. I'm sorry. I fouled that up. This isn't 13. This is 1.99 times 10 to the 24. 10 to the 24 carriers per meter cubed. And the size of an atom is 10 to the minus 10-ish. So that means the volume of one atom is 10 to the minus 30. Anyway, I thought I would get a reasonable answer, but it seems that my numbers just must not be quite accurate. Just so you know, typically the current in a wire, the speed at which electrons move in a wire is something like a meter per second. I mean, it might be 30 centimeters a second, it might be 1.3 meters per second, but it's something like a meter per second, which is kind of interesting because you turn the light switch on and immediately the lights pop on across the room. But the individual electrons they only travel about 1 meter a second. So you can say, well, how can the light pop on the other side of the room so quickly? And what's happening is, you're right, individual electrons take forever to kind of wander through. But because these are charged particles, the minute one moves, all of the neighbors move. And so it's kind of like a game of Plinko, or not Plinko, like a domino, chain reaction of dominoes, where individually they only move a little bit, but the pattern moves out across the room much faster than they separately do. That's kind of the idea. Okay. All right. The last concept I wanted to go through was charge conservation. what does it mean in terms of this new quantity called J, the current density? So what it means is the following. Okay, so let's imagine that I have a volume. Okay, so it's a 3D shape. So I have a volume, and I'm just going to call it V. And then the boundary of it is the surface sigma. And so the way we say that is we would say the boundary of V is sigma. This doesn't mean partial derivative. It means boundary. It just means what you think it means. It means the outer surface of the volume is what we're going to call sigma. And the idea would be this. The idea of charge conservation is the following. Imagine you had some charge on the inside inside this volume. And then imagine that the volume lost charge. Well, it had to go somewhere. And what that means is that in order for the volume inside to lose charge, then there must have been a net flow through the surface. And the amount of charge per second that leaves through the surface must correspond to the decrease per second in the interior. That's the statement of charge conservation. So what we're going to say is that minus the time partial derivative of the charge on the inside, so the time rate of change on the charge on the inside, and if you lose on the inside, that means you have positive current going outside. So that's going to be current through the surface sigma. So usually people label the current through the surface like that. Or if I write the charge in terms of a charge density, I would say minus the integral of the partial derivative with respect to time of the density integrated over the volume equals, and write the current in terms of a current density, the integral of J dot dA, where this flux integral is over the boundary surface, and this integral was over the interior volume. This is the statement of charge conservation in this language. It says that what you lose on the inside has to match the stuff that went through the surface. And then I've just rewritten it in terms of density, charge density, and current density. This equation, as written, is called the continuity equation. And for those of you studying mechanical engineering, there's a perfectly equivalent equation for like momentum flow, current, basically you'd have like a certain amount of mass inside a volume and in a region in a fluid flow, and you would say, okay, well, the amount of mass inside this region, so if I lose mass on the inside, then you have to have mass crossing the boundary of that region, and momentum is going to be the thing, is going to play the role of like a current density there. So it has a perfectly good correspondence with fluid flows, and it's also called the continuity equation in that context as well. Okay, the main thing is don't forget the minus sign. So you want to say that the current measures the outward flow, but outward flow represents a loss on the inside. Okay, that is kind of the formal definition of current. We'll see a little bit more with current density J. Most of the time we will work with I, just the overall current in a wire. the thing that's familiar for linear electrical circuits, but it's important to know about J, especially if you go on to take other kind of higher level courses in electricity and magnetism. All right, see you guys next time.